All right, what's on the bench today? It is a power rail probe. Pretty rare piece of test equipment, and we'll be going through this. Now, where did this come from? It was sent into the channel by a gracious viewer of the channel. He was working, he's an electrical engineer, and he was doing his job, and he had to be able to measure power supply, ripple and noise. And I've been asked many times on the channel to measure power supplies that I review for their power supply and noise figures. And I've always said no, because I don't have the right equipment to do it. It's actually a very difficult measurement to make. And you need one of these. And so I'll be able to do that now in the future. So what is this thing? So power supply, ripple, and noise. You imagine you have a waveform. It's going to be a DC waveform, right? And there'll be ripple and noise on top of that DC. And you want to measure this noise. And it's very small, so you want to change the gain of your oscilloscope so you can see that. But it goes off the screen. And you say, oh, well, you just push the AC button on the oscilloscope and then it drops down, and then you can do that. Well, there are problems with doing it that way, okay? And what this magic box does is it takes that DC offset and subtracts it to 0, and then you're left over with the ripple and noise, and then you can turn up the gain of your oscilloscope and you can see that thing. And this knob here adjusts the offset. Okay, so you put in your DC, you adjust it offset to 0, and then you can run this into the oscilloscope, and then you can measure really good things for power supply rails. Now, the big boys make these things. So Tektronix and Keysight and all the others make power supply rail probes for their fancy oscilloscopes, okay? In fact, this fancy oscilloscope, you can use a Keysight power supply rail probe, and I'll show that. I don't have one, but I can show some pictures of it. That plugs into here. It uses this fancy connector at the bottom that displays power and stuff, and it uses basically the same circuit as this, but inside the probe. And there's a bunch of tricks you need to do to make it good. So anyway, so this guy needed to do that at work. And so, I don't know, he probably went and asked his boss, hey, can we buy one of those, $20,000 oscilloscopes? And then, oh, by the way, we need to buy a $7,000 probe, to do the, anyway, his boss probably says, no, is there another way you could do it? And he goes, well, we might be able to build our own. And so he went on a quest to build his own, and it ended up a big project for him, and he decided to go ahead and actually build things and sell them. Okay, so these are available for sale. So down in the description, I'm going to put links to his GitHub site. This is open source. To his GitHub site, you can see what he did. It's got full schematics and everything, and all of his journey, all of his measurements and stuff. And then also a link to the company he's using to manufacture these things and sell them. So these go for, I think, about $350 instead of $3,500. So they're like 1/10 of the price of the big boy things. And yeah, they'll get you most of the way there. So let's talk about what's inside here, and then we'll open it up, take a look at it, we'll put it to use, and a whole bunch of other stuff. So first of all, let's talk about what's inside this thing. Okay, so before this guy worked on it, there was another guy who worked on it, and he wrote up a nice article in Circuit Seller years ago. And so it's a really nice article on how this thing works. The GitHub site of this guy points you to this paper that is the Circuit Seller paper. But this is the original Circuit Seller schematic, okay? So the way these probes work is you have an input and an output, and there's an AC path and there's a DC path, okay? So the AC path goes flying through this capacitor and just shoots right through. And then you can take the DC voltage here and sum in an offset. So now you have 0 volts here, right? You can sum that in. And then you can come along here and inject it back in. So now you have a 0 volts here plus the AC that made it through. So you're stripping off the DC, you're dropping it down, you're bringing it in, and then putting back AC back into it. So that's the way this thing works, okay? So there's a balancing act of making sure the thing has a flat response in the frequency domain. And that's where all of the tricks come in. And so it relies on a couple things. It relies on a clever, architecture and modeling and stuff. It relies on a really, really low noise amplifier. This op amp here, we'll take a look at that data sheet. It's an LMP7731. Yeah, so this is basically what you want inside your power supply rail probe, okay? So let's take a look at what Keysight did, okay? So over at the Signal Path, the YouTube channel Signal Path, he did a great teardown of a Keysight power supply rail probe, and he opened it up and we can see inside. So these probes have a small PC board in them, and the back side of the board has a microprocessor and a D to A, which generates the offset voltage you want to apply. And then the top side of the board has that schematic that we just saw. So let's take a look at, he has some great photographs that I've copied off of his YouTube video. Again, I'll link that down below. And so here is a photograph that he had on his channel. And you can see there's an input and an output. All right, and then this is all shielded. Make sure that no noise gets inside, okay? But just the layout of the PC board should look very familiar to the circuit here, right? There's an AC path, that's right here. It comes in, it goes through a resistor and a capacitor, and then it goes right out to the output, okay? So there's there's that. And then the DC value goes through this resistor down to the 2 op amps. So here are the 2 op amps. And then it gets summed back in right here, gets summed back in, and DC offset gets canceled here and goes out. So this is the exact same circuit. It's probably got different components and different, magic and stuff that they did in theirs, but it's basically all the same thing. And so that's how Keysight did it. All right. So let's take a look at our unit. Okay, so on the front we have the DC offset adjust plus and minus 20 volts. The probe, that goes off to whatever you're measuring. The BNC over to your oscilloscope, and then there is an on and a off. So, and it says charging. So in order to get the lowest noise, you can't have a power supply attached to this thing, okay? So it's got batteries inside. So this thing is battery powered to have 0 noise influence from the outside world, okay? So let's open this thing up and take a look. All right, I've taken the screws out of it, and the PC board just slides out. And you can see the batteries. So we have a plus and minus power supply in here. And then let's see if we can find the magic circuit. Oh, it's on this side here. All right, so this is the input. This is the output. Here are the 2 op amps. Here's an inductor. So this is basically your circuit right here. This looks like some regulation for the batteries, so you have a constant regulation on the batteries. What's it say here? So here's some of his information. Here's the GitHub site. I'll put a link below. Like I said, low noise power rail probe, max offset plus minus 20 volts, active signal plus minus 1, active impedance 50K. So that's another thing that these probes allow you to do, is allow you to measure a power supply circuit without touching it much, right? You only have 50K touching the power supply, so but it still has the bandwidth and stuff that you need. Attenuation max is 1 to 1.2. So it's a 1-to-1 probe, ideally. And there are some other funny things in here. I haven't looked at the whole schematic yet, but basically, this is what we got going on inside. All right, so this is his schematic. Here's the input, capacitor, output. Here's 50K coming into the offset. Here's the offset, sums it in. Here's the driver, goes to the outside. So exactly the same circuit. He's changed this op amp to an OPA 322, which is really nice. He's using the lump 775031 though. It's got some protection diodes, make sure things don't go off too far. Agilent also had some diodes to make sure it went off too far too. If you look, there was some diodes in there. It doesn't matter. But everybody's kind of doing the same thing. He's got some test points here for testing or probing or whatever, for maybe for production or something. So let's button this up and we'll try it out and see if we like it. All right, I have it hooked up. It came with BNC cables, which is nice. So one cable is going to go over to a power supply. So you got to make sure that you're completely shielded at all times. So this comes over and it goes into a adapter here. Let's see. I don't want that in there. I don't want these wires hanging out. So take those wires off and put this directly in here. So this is a BNC to banana jack adapter. I'll make sure that goes in there. All right, so we have it hooked directly up to the power supply. We'll turn on 5 volts. So we have 5 volts going into the probe, okay? So now we've got the probe going. Then it goes into the scope. All right, so we need to go over to the scope. I'll rearrange things to get rid of the glare, but just a second here. The scope needs to be set up for 50 ohms input, okay? So here we go, 50 ohms input. Okay, now we're good to go. Let me rearrange things a bit here. All right, now I can adjust the offset. So here's me twiddling the knob on that box, and I already had it set to it. So I'm at 1 volt per division, so here's -1 volt, +1 volt. Anyway, I'm gonna put right here around 0, and then we can start zooming in. So here's 1/10 of a volt per division, and I'll readjust it. And here's 20 millivolts per division. I'll adjust. Now it starts getting quite touchy to adjust. It is a 10-turn pot, but it's starting to get quite touchy to adjust. I'd like to see a little bit better ability to set that. And then we'll go here to 10 millivolts, 5 millivolts, 2 millivolts. Okay, so this is 2 millivolts per division, and we're seeing quite a bit of noise, okay? Now, you say, oh, it must be a terrible power supply. You've got plus or minus 2.5 or whatever's. So that's because of my stupid LED lights. So watch me turn off the lights and watch this thing go, and now it's much smaller, okay? And so there's some weird things that go on. Every once in a while, you'll see a weird little spike there. Let's zoom out. There, see that spike? I believe that's a data transmission from something in the room. It might be my cell phone in my pocket. Might be some Bluetooth somewhere. I don't know what it is, but it is definitely not from the power supply. So usually when you're looking at power supply data sheets, they are specified at 20 megahertz bandwidth. So we'll set the scope to 20 megahertz, and you can see the numbers go very, very small. Remember, this is 2 millivolts per division, so that's very, very, very small. If you did a voltage RMS on that, it would be quite tiny. So the power supply itself is unloaded, okay? So this is what it looks like unloaded. And then let me load it with 1 amp, okay? And so I'm going to add a 5 ohm resistor, and we will put this back together. together. And there we go. Now it's under load at 1 amp, and you can see the noise really didn't change. Let's see if I can get the offset a little. Yeah. So you can get the offset close with the box, and then you can go to your oscilloscope, and you can use the vertical on your oscilloscope to kind of zero it also. But yeah, that looks pretty good. But the claim to fame of these probes is, yes, you can use them this way, and that's great. That's what I want to be able to do. But they also have, I think this one is still around 500 megahertz of bandwidth. So I can still take my oscilloscope and I can open it way up. And the reason that you want to do this in certain circumstances is to take a look at super high frequency noise. Because a lot of circuits look fine at DC, but they might have this really high frequency noise in it that you just couldn't see. Let's zoom way in on it. Yeah, so there's some little things happening in there. You see these little glitches every once in a while. So that's what it's really good at. It allows you to do a DC offset, plus it allows you to still have super high bandwidth on the probe to be able to see these little spikes that might get in the way of fancy high-speed circuits and stuff. Kind of out of my realm. I haven't really designed in this space, but let's turn the lights back on and see what happens. And boom, there we can see the switching noise of the LEDs, the DC to DC converters on the LEDs, and yeah, switching power supplies, I should say, on the LEDs. So yeah, I should spend some money and put in some really low noise lights in my garage. All right, let's see if my load's getting warm. No. It is drawing an amp though. All right, so that's kind of my first look at this thing. I really do like it. It seems really high quality. I think for $350, if you need something like this, I think that's a steal, because otherwise you're looking at $3,000 to $4,000 to get it from Tektronix or Keysight or somebody like that. So a nice device to have. And there's some good videos online about power supply measurements and stuff. You need to take a lot of care. One thing that this doesn't do is oh, I forgot to show the op amp. Let's just show the op amp first. All right, this is that LMP7731. And take a look at it. It's 2.9 nanovolts per root hertz. That's that's small. 2.9 nanovolts. Input voltage noise, at 3 hertz we have 3.3 nanovolts. At 1 kilohertz we have 2.9 nanovolts. Open loop gain 130 dB. A gain bandwidth of 22 megahertz, so it's a screamer too. Fast slew rate, blah blah blah. 1.5 nanoamps. I mean, this thing, it's rail to rail. Yeah, this is a super nice op amp. So anyway, that's what's on the front end there. The one thing that's missing in this, if you maybe need to go the next step, it's common mode noise rejection. And I've seen systems where they take the power supply and they run it into a diff amp that has really good differential rejection. It's about a $7,000 instrument to do that. I imagine, though, you could put in a differential amplifier inside this thing, like another one of these fancy, $20 op amps or whatever, to do the actual common mode ripple rejection or common mode noise rejection and stuff, and add that as a second condition of this device. All right, so as I said, links down below. Go to his GitHub site. He's got a bunch of information there. He shows you his journey of looking at making the bandwidth flat, lowering the noise, and coming up with this device. So yeah, thanks again for sending it in.